3 of continuous charge distributions, in which we'll be looking at a ring of charge. All right, now this is example 2 in your notes packet, and we're going to go through the exact same steps, but some of the results are going to be a little bit different because, of course, the geometry is different here. So having chosen the correct equation, I now have to go through, choose an origin, and draw the charge element dq, and then put it in terms of stuff and define all my variables. That's, in this case, going to be a little bit weird, because where would I put the origin? Well, you can kind of put it wherever you want, okay? But remember, the visual here is this is like a ring. We're looking at it from the side. So it's coming out towards you, going back in. Let's say this is the near edge, this is the far edge back there. I'll put my origin at the top for really no particular reason. And then I'll draw my charge element, how about here? All right, there we go. Okay, next thing is defining dq and r, and then also r hat. R is going to be the distance between a charge element on here and the point where I want to find the electric field. All right, that's what little r is going to be. dq is going to be the same lambda r d theta, but it's in terms of the actual radius of the ring, not this r right here. Okay, the amount of charge on some particular section is based on the arc length, right? And so that's based on the radius of curvature of the actual ring, not on the distance from the ring to the point. All right, little r. All right, little r is going to be this distance here. And we can say that any point on the ring is the same distance away from that point. I've drawn it from my origin in this case because it's a little easier to see the geometry there. But from dq, it would be the same idea. Okay, so that r is going to be, well, let's see, based on Pythagorean theorem, it will be the square root of r squared plus x squared. Okay, so I'll put that in down here, and of course, since it's getting squared, the square root will go away, and we've got that. All right, now there's two more things to take care of here. One of them is what is theta, and the other thing is what is r hat supposed to be. All right, now theta is not this angle. We're going to have to call that angle phi, okay, or whatever your favorite Greek letter is, but it's not going to be theta. Theta relates to, since it's for the charge element, going around the circle, right? So theta actually is this angle, right, going around the circle. So that is theta, okay? Phi is this other angle, which relates to the angle between the origin, or the center of the circle, and the edge of the circle, and this point here where I wish to find the electric field, right? That's what phi is related to. So it's not the same as this angle theta here, right? So like when we did the half ring of charge, right? And we were finding the field, say, at the focus of the ring, we're going to have to talk about r hat in terms of cosine theta I, cosine phi of I and sine phi j. Okay, so break it up into cosine and sine. Like last time, we can say that the x components will add, right? This charge element up here makes a field like that. This one down here in the bottom would make a field like that. Also recognize, though, that there's not just x and y. In this case, we have to talk about the z components, because a charge element way out here, right, would make a field that would point into the board, whereas one a little bit into the board, right? Also forwards, but into the board. And a charge element on the other side of the circle would make a field going out of the board in addition to, say, forwards. So essentially then, what these charge elements around this ring are going to do is make like a cone of electric field elements, right? Which is difficult to draw, but you can imagine it, right? They're making a cone of field elements. Based on symmetry, the y components and the z components are all going to cancel out. Thank goodness, because if they didn't, we'd be up for a much more complicated integral, and I don't really want to think about that. Okay, so back to the x components. The x components then are going to be related to cosine of this angle phi. So let's rewrite our integral with cosine phi in there. All right, now phi, fortunately, doesn't change. It maybe kind of looks like it changes because the it's kind of hard to draw the geometry, from there to there, right? But it's the same angle phi from any point on the ring. Okay, so phi is one thing. So that means cosine phi is one thing, which we can define in terms of this reference triangle I've got here. Cosine of phi is going to be related to adjacent and hypotenuse. So cosine phi is going to be replaced with x over square root of r squared plus x squared. That's what cosine of phi is going to be. After I sub that in, here's what I will have for my integral. All right, the trickiest bit in the simplification here is the r squared plus x squared to the 3/2 power that I wrote down there. All right, don't panic. You'll actually see to the 3/2 power come up a lot when you're doing integrations to find electric fields and such. And that's coming from the fact that this is r squared plus x squared to the 1st power, if you like. And this is r squared plus x squared to the 1/2 power. All right, well, 1 plus 1/2 would be 3/2. And so therefore the denominator is r squared plus x squared to the 3/2 power. Okay, now this integral looks horrible. Like it's going to be just a monster, right? But actually, thing is, I'm integrating with respect to theta. None of those things depend on the value of theta, right? X is this distance away from the focus of this circle of charge. R is the radius of the thing. Lambda is a constant. So nothing depends on theta. Theta is just we're going around the ring, all the way around. And so everything except for theta is a constant in this integral. Because none of them depend on theta, we can just drag everything out of the integral, right? Remove all of the constants. And the only thing left in my integral is d theta. I hat, whatever. All right. The bounds on theta. In this case, are actually going to be simpler than before. We don't need to be like, well, 0's in the middle, and then I get to find it. Here's my origin. I'm just going around the circle. 0 to 2 pi. All right, so when I get all done integrating, integral of d theta is just theta. I'll plug in 2 pi minus 0. And so the integral then is just going to be all of this times 2 pi. I have nowhere to write it. So here goes. All right, in case anyone noticed in the previous step, I somehow dropped the 3/2 by mistake. So I added that back in, and this is our finished integral right here. All right, the text of the question also asked us to turn this into something that was in terms of Q. I'll leave that as an exercise to you, but that answer actually ends up being nice and simple. It just turns into KQX up there in the denominator over the same exact stuff in the denominator. Okay, so you can explore that outside of the video, how we get from this to that. All right. Let's go ahead and do part B, find the electric potential. I will ask you to pause the video and again, as we've done before, see if you can set it all up and then resume the video when you think that you've got the answer. Remember, with potential, it's a scalar quantity. There's no r hat over there, so that means that you won't need to have a cosine or a sine of phi at all. Everything's just going to be in terms of distances. All right, so pause and then resume once you think you've got it. And of course, you can put this in terms of Q instead of lambda. That answer looks like KQ over square root of r squared plus x squared, which, by the way, at the end of the previous video, I said, that should look familiar, KQ over R. This is actually doing the same kind of thing. Remember, since potential is a scalar quantity, sometimes you can sort of shortcut to the answer. As long as you don't have different bits of the object or different distances away from the point where you want to find the electric potential, the question with electric potential just boils down to how much charge, how far away. So if the amount of charge that you have is Q, whatever that is, and all of it is this distance away, then the potential is going to be KQ over the distance that it all is away. In other words, we didn't really need to do calculus to find the electric potential. It's important to talk about how to set it up because the AP might expect you to do that. Or other times in later coursework, you might find, oh no, you've got to do a line of charge and find the potential there. And this actually does get complicated because different points on this are different distances away from that one. But as long as you have a ring or a circular curve or whatever, semicircle, where you want to find the potential at the focus, that's super straightforward because it's just KQ over R, where R is the distance that all points on the object are away from that point. All right, the last bit that I want to look at with this question is, it says, show that the electric field is the negative derivative of the electric potential. I'm also going to show this one in sort of like a stop motion kind of a thing. But basically, I'm just going to take the derivative of this, which will involve quotient rule, and then show, oh, look, it's the same as that. Okay? So go ahead and try it, and then follow the various steps. Actually, interrupting myself. It's not necessarily going to be quotient rule. You could say that this is r squared plus x squared to the negative 1/2 power, and then kind of treat it like a power function. But remember that there will be chain rule involved. Okay, continuing. All right, here we are at an intermediate step. Almost done, just got to simplify it. All right, now there was one thing that I missed in the previous couple of seconds. That was, this is to the negative 1/2 power, which means actually from power rule, this should say negative 1/2. Okay, fine. But the rule is that it's the negative derivative. Okay, so the negative derivative means all that cancels out, and it proves what we said it would. Great.